Yes, hello everyone, and yeah, welcome to the second half of this meetup. So my name is Petter, and this is my fourth talk in this meetup group. I had a pretty good track record of doing one talk every year, and this one I actually started in the spring of 2020. So at the time I thought that maybe there's a chance that there will be a meetup before the end of 2020. That was a bad misprediction, it turned out. But so it's great to finally get this out of the door, and I hope you enjoy it. It's actually quite an ambitious talk. I chose to combine three different subjects: functional programming, text parsing, and C++20 features. So I hope there's going to be something interesting here for everyone. And don't be too worried if you're not an expert in all of these fields. We're not going to go extremely deeply. But yeah, I have a lot of slides, so if it might be good to remember there are slide numbers. In case you see something you want to bring up at the end, you can check the slide number. So yeah, let's start. And I want to start this with a question, and this is a question for you. So it's just an open question. There's no right or wrong answer here. It's just something you can think about, form your own opinion, maybe discuss later. But so C++ is kind of a different language from many other programming languages, I think, because it doesn't promote any particular style of programming or paradigm. In fact, even if you go back to the early 90s and you would ask Bjarne Strostrup, the creator of C++, what the language was all about, this used to be his kind of standard answer. So C++ is a general purpose language with a bias towards systems programming that is better C, supports data abstraction, supports object-oriented programming, and supports generic programming. And this still holds true today. But kind of a problem with this is that a lot of people really didn't get it back then and still don't, I think. For example, many people say C++ is an object-oriented language. And actually, if you listen close to what Bjarne Strostrup says, when he describes C++, he never actually says it's an object-oriented language. He says something like, it's a language that supports an object-oriented style of programming. And it's a little bit different. Like, the language has tools within it to write efficient Simula-style object-oriented code. And that's great. If that fits your problem, well, then go ahead and use those tools. So that will help you make a better program. But that's an optional part of C++. You don't need to use it. And it's the same with all these styles. And of course, with every new version of the C++ standard, there are attempts to make C++ more pleasant to work with in each of these different styles, and there are new features that try to integrate them better. You can also combine them in interesting ways that are not easy to do in many other languages. And so something I have noted is that, like with the more recent C++ standards, more and more new features take inspiration from functional programming. So that's the question. Could we even claim that with C++20, it's a language that also supports functional programming? So I don't know. I don't know what Bjarne thinks, and I don't know what you think. It's kind of a vague question because, what's your definition of functional programming? What's the features from functional programming that you think are essential in a functional language? So yeah, it's a little bit difficult, but that's what I want to kind of explore here. And so what is functional programming then? Well, I'm sorry, I don't have a clear definition. To me, it's more like, I think of it as a collection of ideas. And so here are some of the ideas I think are important. It's not all of the ideas, of course, but so first of all, in functional programming, usually you tend to work with immutable data, right? So constants, which has many advantages. Often constants much easier to reason about in the code. It's great if you want to write parallel code, right? If you want to share data across multiple threads. If it's immutable, you don't have to have any locking mechanisms, so you don't get any race conditions and stuff like that. So it's also great for performance. So I guess that's one reason why functional programming is really popular these days. So another idea is that when we say functions in functional programming, it's you usually mean pure functions, meaning first of all functions that are equality preserving, meaning that if you call a function multiple times with the same data, you always get the same result back. And also there should be no side effects, at least not any side effects that you can observe externally. So essentially you want to think about functions like functions in math, like a static mapping from inputs to outputs. And you can cache function calls and so on. And third idea is, so functions in a functional language are kind of first-class citizens of the language. They are objects also that you can pass around as inputs to functions, and you can make functions return new functions. So those are called higher order functions. And lambdas certainly help in that area. Makes functions composable, very important. And then often in functional programming, you're also not allowed to write like multi-statement functions with variables and so on. So if you want to do something iteratively, you can't write a loop. You have to use recursion, which can be difficult sometimes. And the final idea here is perhaps the least familiar to C++ programmers, partial function application, which is if you have a function with a certain number of arguments, you don't have to call it with all of the arguments. You can pass just a few of them, and what you get back, instead of the normal response, you get back a new function, which when you call that with the remaining arguments, you get the original function call. So if you're familiar with something like standard bind, this is the same idea. We'll get back to that later. And of course, there are many, many popular programming languages that have made these kind of features core features of the language. So I have a few of them here. Just curious, like how many of you have used any of these languages and you recognize them? A few people, yeah? So,
I only see the symbols. What are the names?
Yes. So you know this one? It's Clojure, yeah? This is Elixir, Elm, Erlang, F#, Haskell, Kotlin, Scala. So now you know some logos. And of course, the third one, it's called Elm. Yeah. So you might have heard about these languages. And they are very different languages, like they are specialized for different things. Some of them are more pure functional, some allow different styles and so on, but you have a good selection of these. And I don't think many people would put C++ in a list like this, right? But that's what I kind of want to explore. So I was interested in seeing, like, could I use modern C++, C++20, to write some code, to write a program that can artificially limit myself to pure functional programming so that the code would be easy to basically translate to any of these languages. Just to see, you know, it's not, keep in mind, it's not necessarily a good use of C++, it's to test the limits of the language. And to do that in a good way, I needed a good problem, something that's practical, not too theoretical, and not too simple, something that you might actually use for something, for something real. So, so here I got some inspiration from a YouTube video. How many of you know about the Computer File channel? Have you watched it? Yeah. I'm not surprised, like a lot of people here have seen this channel. It's hugely popular. I checked, it's past 2.1 million subscribers. So for a channel about computer science and programming, that's kind of awesome, I think. So the format of the channel is usually like 10 to 20 minute interviews with various computer scientists that talk about something they're passionate about in computing. And yeah, it's fun to watch. It's like very easy to get a glimpse into what they're working on, and even if you're not a programmer. So this guy is on the channel sometimes. So his name is Graham Hutton. He's a professor of computer science at Nottingham University. I think he's kind of famous in the Haskell community. He's written some important papers on Haskell, and he is also author of this book, which is actually a great book if you want to learn some Haskell programming. I think this is a great starting point. So in this video, what he was doing, he was showing how to use Haskell to write a program that could simultaneously parse and evaluate mathematical expressions, simple as strings, in just a few lines of very beautiful looking code. So I thought this was really cool example of functional programming used to do something interesting. So, but there was a big problem, and the problem was he was using Haskell. And I don't know about you, but yeah, I know a little bit about Haskell. I'm kind of curious, but I never actually written real Haskell code. So I felt that to really understand what was going on, I needed to sort of write this in C++ and see how it would work in C++, if I could write something similar and compare it. So that's what I set out to do. So here's a problem that we're going to try to solve. So, so the idea of a parser is that, so we have a string like this, simple mathematical expression with multiplication, addition, and parentheses. That's all we're going to take as input to a function, a parser, that should compute a value, like 14 in this case. And to do that correctly, of course, it's not enough to go like from left to right, tokenize this, because we want to respect this convention in math that we do multiplications before additions, unless there are parentheses. So you can think of this as, the parser should understand this as a binary tree, right? Where the leaves are the numbers, and these binary operators have to be applied in a certain order. Okay, so before we can write the parser, we have to sort of grasp this syntactic structure. And that's usually done in some form of language to describe it, usually some form of extended Backus-Naur form. And it can look like this. So this particular syntax was, this is the original extended Backus-Naur form invented by Niklas Wirth. He proposed this in a short article in Communications of the ACM in the 70s. You should all know about Niklas Wirth, of course. Turing Award winner, creator of Pascal and many other great languages. He's written many great books. He's still alive, by the way. I checked his, like last Tuesday, he turned 88. So still going strong. And here is a little grammar that explains how we should do the parsing. So you sort of read these grammars from the top to the bottom. So at first we have expr, that's the whole expression, and that consists of a term followed by a plus sign followed by another expression, or it could be just a term. So quotes means it's a string literal, and the pipe character is its choice. So with just that rule, you can see you can recursively describe the whole expression as a finite sum of terms. So then we parse the terms, the second rule, so that's the same thing, but yeah, it's a factor, a multiplication sign, a term, or a factor. So since this rule comes below, that will give us like we do the multiplications before the additions. And then we have a factor, which is either a parenthesized expression, so this is like going back to the top, which will allow you to override the evaluation order, or it's an integer. And then we have an integer that could be a negative number, so optionally there's a minus sign, right? So square brackets means 0 or 1 or whatever, or what's inside, followed by a digit, followed by more digits. So the killer braces is a loop. And then of course the digits could be any of the 10-digit symbols. So this is a nice little grammar that describes this language. So now the problem is we just need to take this and write a parser based on this. And of course there are many ways to write parsers. So I'm just going to talk about two here. So one approach you can use is you can use a parser generator, and that's just a tool. It's actually a parser itself, so it can parse grammars and turn them into source code for the parser that in your favorite language. it's not all the code, like you have to add the types of the things you want to parse and so on, but you get most of the job done. And then you just compile it and you have a parser, right? So another approach, if you don't want to use a tool, if you want to actually start from scratch, so one approach that works great with functional languages is to write a parser combinator. And that's a kind of parser that I'm going to talk about. So parser combinator, you just write functions. And there's two kinds of functions. The first kind is they're just called parsers. And they can be, you start by writing very, very trivial parsers. So like, they don't parse the entire input, they just parse maybe a single character. So you start very simple. And then you need to write a few generic higher order functions. So these are functions called parser combinators, because you can take multiple parsers, combine them in different ways into more advanced parsers. And you just need a few of those to do some generic stuff, and then you can sort of build up more and more advanced parsers from those as your basic building blocks, until you can parse the rules of your grammar. Right, so let's look at the first kind here, the parsers. What should a parser look like? So this is basic idea. A parser is a function that takes a string. And since we work with immutable data here, we can use standard string view. That's a great type, has a great interface for this. And it should return a parsed thing of whatever type T you like. It depends on what you're parsing, right? If you're parsing a number, maybe you just want a numeric type. If you parse a identifier, maybe you want a string. If you parse an entire programming language, you maybe want some kind of abstract syntax tree, some data structure that you're going to pass on to the next stages in the compiler. So that's a basic idea here, but it's a little too simple. First of all, like the parsers shouldn't, except on the top level, the parsers don't parse all of the input. So we have to describe somehow how much of the input we have parsed and what is left over for the next parser. And so a very simple solution is instead of returning a thing, we can return a standard pair of the parse thing and the string view, whatever's left over. But there's one more thing to fix. And the second thing is what happens if the parsing fails? What if you give it a bad input? Right, what should you do? How do you signal an error? So there are multiple solutions. The one I have chosen here is one of the simplest ones. And common one. Instead of returning a pair, we can return a std optional pair. So we just wrap that pair in a std optional. So we get that extra empty state, which can represent the parsing just failed. So there's no information why it failed. We don't particularly care here, just to keep things simple. And note also that there's no assumption about how often we're going to fail. In reality, it's going to be quite a common and natural thing to fail. So this is actually perfect for std optional, just the kind of thing std optional is designed for. Okay, so that's the actual function signature of parser. There's just one thing I don't really like here, and it's very long return type. And the only thing that varies is the type of the thing, right? So we can make it a little bit shorter with an alias. So if we just define an alias template, which are called parse T, so T for type, it's a little easier to read. And note that, of course, it's just an alias. It's not a new type or anything. It's just a different name for the same type. I kind of prefer to view this in a more functional way. So I prefer to view it as an example of type constructor. So what's that? Well, you hear about type constructors a lot in Haskell. Actually, a type, it's very simple. It's just what it sounds like. It's some kind of language mechanism that you use to construct a new type from existing types. So in a sense, you can think of this parse T of T return type as you're kind of making a compile time function call. You're passing in a type, and it returns a new type constructed based on that. So, and in some sense, this alias is like a function that defines what that is. So std optional and std pair are both examples of type constructors in C++. They're not types, they're templates which you have to instantiate it with a type, and the compiler gives you a new type from them. So yeah, if you don't see it, you don't see it. It's not terribly important, but I think it's interesting that like we're already doing some functional programming here at compile time, operating on types. But yeah, so how do you remember the function signature of a parser? Maybe you've seen this one before. It's a nice little rhyme, comes from the Haskell community again. So a parser of things is a function from strings, or string views, to an optional pair of things and strings. That kind of gives you the essence, right? So I really like that. So really what is a parser? Is it a particular type? No, because functions have types, right? But there are different functions have different types. So this is like the set of all functions that have this interface and do parsing. And that's, to me, that sounds exactly like the definition of a concept, right? So how many of you have used C++ concepts so far? Like for real? Yeah? Few people, that are really good. Concept is my favorite feature from C++ 20, and the best kind of high-level description I know is in this book, From Mathematics to Generic Programming, which says a concept can be viewed as a set of requirements on types, or as a predicate that tests whether types meet those requirements. And the requirements concern the operations the type must provide, so interface of a type, but also their semantics, what they do, and their time and space complexity. A type is said to satisfy a concept if it meets these requirements. So something to note is that a type is not aware in any way that it satisfies a concept. It implicitly satisfies a concept by having the required interface as part of its interface and behaving in the right way. Which is actually great, because if you think about, so you can define a concept and it will be satisfied by types that you already have. You don't have to, like with inheritance, explicitly state that it inherits from something. Here you can even write a concept that describes a built-in type or standard library type or third-party library type that you use that you cannot change. And also the C++ 20 standard comes with a bunch of library types defined that we can use for basic things. And in a standard, they're just described as components that C++ programs may use to perform compile time validation of template arguments and perform function dispatch based on properties of types. So that's kind of, doesn't explain anything about concepts, it just tells you something what you can use them for. So with C++ 20, we got this as a core language feature. Instead of just describing it in documentation, we can actually do some type checking at compile time. And I'm going to use a few of the standard library concepts. All in all, I'm just going to use 5. And I'm only going to talk about 2 here. So the first concept is called standard same as. This is the first concept in the standard, very simple. So you can probably guess just from the name what it does. It checks if 2 types are exactly the same. So if you put standard same as int, since int is the same type as int, this will be at compile time the value true. So you could do a static assert like that. And int and double, since they are different types, that would be false and that would fail to compile. Of course, in real code you wouldn't have a silly check like that, but you might have a check if you use an alias or something depending on template parameter, then it could be useful. The second concept I'm using is very important for functional programming. So it's called regular invocable. And perhaps that name is a little bit confusing, but it helps to think of that as meaning pure function, basically. So it's a variadic concept. It takes, at first it takes a type of function or a presumed function, like a to I, for example, and then it takes the types of its arguments. This is actually quite kind of similar to what Arne was talking about with the type traits, but now here it is as a concept instead. You have to be a little bit careful with this concept though, because if you check a function like rand, which takes no arguments and clearly is not a pure function, right? It has side effects. It will still compile, and that's because concepts can only check syntax. So there's a limitation in the language here that if you have a function, you cannot somehow annotate it that it's if it's a pure function or not. And the concept checks are only on the interface level. So that's good to know. Another thing, like why is it called invocable? Why didn't they just call it callable or function or something like that? So that's related to another problem with C++ functions. The problem is there are so many ways you can define a function in C++, if you think about it, right? You can make free functions, but you can also have function pointers. They're also callable, standard calls them callable types. You have member functions, pointers to member functions. You can have pointers to member data, which can be callable in turn. You can have class with a function call operator. You can have a class that's convertible to a function pointer. You can have class inheriting from a callable class. You can have lambdas, of course. You can have a library component like std function, std memfun, the return type of std bind. You can have a reference wrapper to any of these things, and you can have a template, and yeah, the list goes on. All of these things, yeah?
What does it actually check when you say no observable side effects?
Yeah, I will explain shortly what it actually checks. So the problem here, all of these are callable, but unfortunately the syntax to call them is not always consistent. You cannot just put name of the thing parentheses arguments like you call a normal function. In some cases the syntax looks a little bit different. So think about maybe if you have a pointer to a member function, there's a special quirky syntax to call that member function. Is that a huge problem? Well, most of the time maybe not, but it becomes a problem if you write generic code. So if you write a template function that takes another function as input, like many of standard library algorithms do that, like find if you pass it a function, the predicate that you want to check. Now you end up with the problem inside the template. How do you properly call that callable thing if the syntax can vary? Now that you can solve either through some really complicated template metaprogramming, so you get a lot of code duplication and miss some obscure edge case, of course, or you can just solve it by passing everything to standard invoke, which was added in C++ 17. So just pass everything into standard invoke and let standard invoke do the metaprogramming or whatever it does to solve that for you. So you get kind of a uniform, kind of ugly syntax, but still it makes the code a lot easier to use. So that's why it's called invocable. Technically what it checks is, can I pass this to standard invoke and will it compile? So yeah, I hope that answers your question. Okay, a lot of stuff here about these concepts, but we actually want to write our own concepts. And with C++ 20, here's how you define a concept. You define them as a template. You can use some types, parameters. Then you use a new keyword concept. The name of the concept equals some compile time Boolean expression. And very lucky for us, it turns out the string literal is a compile time Boolean expression. It's implicitly convertible to true. So technically to the compiler, this is a valid concept. It will compile. But it's kind of a useless concept. It's telling the compiler every type is a parser. So that's not what we want. That's too unconstrained. So we want to describe it more precisely. We want to translate that little rhyme into C++ code. And so now we can do this with the help of our concepts. So first of all, a parser of things is a function from strings. So we can express that as it's a regular invocable that takes a single argument, in our case of type string view. And what about the return type? Well, it should be an optional pair, right? We had an alias for that, return that optional pair. So one way you can express this is with a requires expression. And that's mostly used just in definition of concepts. So that's the other new keyword, requires, followed by a list of parameters, some curly braces, and inside you basically have compile time statements that have to be true for this to compile. So So think of this as you're telling the compiler, please imagine you have an object called result. What's the type of the result? Well, it should be the return type of our function, or presumed type here, or function p. So here I'm using invoke result t, like Arno showed in the previous talk. That is the return type of this presumed function. So if we can get that, then we just need to check what that type should be. And here we can use same as. So we want the type of that result to be a parsed t of something. What's the something? Well, it has to be an optional pair, so we can actually extract the value type out of the optional. That's a pair. And then we take the first type of the pair. That's the thing. So if all of this works out, then, you know, at least syntactically, you have a parser. Okay, so it's also helpful to define a few type functions. And type functions these are just aliases again. The only difference from the type constructor alias is here, this is referring to types that already exist. They are just related to the parser type. So we have the return type, so parser have a result type, which is just the shorter way of writing the return type, or invoke result t. And they have a value type, which is the type of the parsed thing. So, but what's cool here, these are templates, but now we can constrain them with our concept. So instead of saying type name p, I'm saying parser p. So if you try to use this name with an int or something, it will fail to compile. Right, so that's a lot of new C++20 stuff. So now let's actually start writing a parser. So here's my first functional parser. I could have made this as a free function. I just chose to make it lambda. They are handy sometimes. But yeah, it's just function. It takes some input. It returns a parsed character. And it's going to be the first character in the string. So this could actually fail. If you give it an empty string, we should fail. And that we can do with a return type deduction here because, yeah, I have been explicit about the return type. So I can just use the empty brackets as a default constructed optional. Right, it's going to be what we want. Otherwise, we can extract the first character. And we have parsed the first character, so the rest is a substring starting from the next character. Okay, so if you want to, you can actually check here that this function is a parser with static assert. I wouldn't normally do this in real code, but it's good to know that you can. And we can also make everything here is const expert, so we can make a sort of unit test even at compile time, checking that, for example, if we give the string foo, that should parse f and leave the o's for the next parser. If you give it the empty string, it should fail, right? So everything clear? Good. That seems like the simplest thing you can do, but it's actually, there's an even simpler thing you can do. You can just fail. So here's the empty parser. It just takes an input. We don't even need to name it because we're just going to fail. What's interesting about this one is there's no way to tell, even if it's empty, it has to have a type, right? So there's not one empty parser. There's one empty parser for any conceivable type you have. So you have to call empty and with a type. So the empty char of foo, that will be an empty parsed char. Empty int of empty string will be empty int, parse t of int. Okay, so very basic parsers. These are actually going to be the only parsers we need to get started. So let's go to the parser combinators. And so here I'm jumping right into the concept that describes them. So now I hope you can read what this does. So parser combinator is just a function that takes any number of arguments, can be 0 arguments actually, if you want to, and its return type, so the invoke result t, should be a parser. So it doesn't have to actually combine multiple parsers. You can have a parser combinator that takes nothing. The important thing is that it returns a parser. And parser combinators also have a value type that I have defined. And here I'm using a requires clause to check that. That's the most general form of concept check that you can do. So that is different from a requires expression. It's just the keyword requires followed by some compile time Boolean expression, usually a concept. So that's a parser combinator. And let's look at an example. So suppose you want to parse an input that should start with a certain string. So then it could be useful to create a parser for just that particular string. And that we can do with this function stir. So it takes a string view of the thing you want to match. So it takes a string view as input, but it doesn't return a parsed thing. It returns this lambda. So it returns a parser, which just captures that string you want to match, so that later when you call it, it will just check if the input starts with that match. That's what we want to see, so we return that successfully, otherwise we fail. So this is using a new feature of C++20. So standard string and standard string view got some new member functions in C++20. One of them is starts with, which is perfect. This is just what I needed for this. All right, so for example, if you want to parse a string, if you call stir foo, you get a parser that when you parse foo bar, you will get the foo successfully. Okay, so here's another parser combinator, and this one is really important, but also, yeah, really basic. The idea here is that suppose you have a thing, any type, an object of any type t, and all you want to do is you want to turn that into a parsed thing without doing any actual parsing. So we're just returning here a parser that captures the thing. If you use that later with some input, if you just plug the thing and input together without actually touching the input. So for example, if you call unit of x, you get back a parser, which makes x the result of whatever you parse. If you use unit of 42, that will be, yeah, you get the parsed int 42, empty string. It can actually never fail because you're not doing any parsing. All right, so this one is the first parser combinator that actually combines two parsers. It's so important that I chose, instead of giving it just a name, I overloaded an operator for this. But don't worry about that. It's just a function that takes two parsers. And the idea is that we want to try the first parser. If it fails, we try the second parser. So here's the first use of std invoke, because we don't know exactly what kind of callable type our p is here. So we just call it with std invoke. And then since the result should be an optional pair, remember optional has an explicit operator bool, so we can use it just in an if statement to check if it's empty or not. And if it's not empty, we are happy. We have successfully parsed with p. But otherwise, we try q. To make this compile, I have to be explicit about the return type here. And I chose to make it the return type of the second parser, because of course these two parsers could return two different types, and that wouldn't work. But it would be okay if the type of the first parser is convertible to the type of the second parser. And that you can check with this concept std convertible to. So that's kind of like same as, so it takes two types, but here it checks if the first type is convertible to the other, implicitly and explicitly, and those two conversions have to be equivalent. So that's a semantic requirement. So then this will work. So also note that since we're returning a lambda, we cannot say what the return type of this function is, because the types of lambdas are only accessible to the compiler. We don't have a name for them. So the return type of functions like this in C++ have to be auto. However, we can, with the concept, we can constrain that auto and say that it should actually have to be a parser if it's a single argument concept like parser. So this is really nice, I think, even if you don't specify exactly what type it is. The important thing is that it's a parser, and you can actually make the code much more readable like that. Also, if you implement the wrong thing, this would fail to compile. So why is it a binary operator? Well, because it's a binary operation. Like it takes two parsers, it also returns a parser, so you could actually string those along if you have multiple things you want to try. So if you combine empty of char with item and unit of x, it's very handy to have an infix operator here. Of course, what would happen if you parse empty string? Well, empty of chars always fails. So that's kind of silly to have there. It's just an example. Item would also fail in this case because there's an empty string. So we would end up just parsing with unit x here. Now, I know it's kind of controversial to overload operators for exotic things. Some people really dislike that, and there's many good reasons to dislike it. It could make the code very terse, but also very obscure and hard to understand. So I'm actually not going to use this directly. I just need it so that I can implement a little helper function here. And that's a function I call choice. So this is using some other nice C++20 features. So it takes a parser and a pack of parsers. And then I'm using a fold expression here. So it's a binary left fold. If you ignore the if const expr, it's just look at the stuff inside of else here. What this will do, so if you call it with just one parser, it just returns it. But if you call it with some additional parsers, it will call my operator, passing in first the parser and the first of the parsers, take the return value, pass it in on the left with the second of the parsers, and so on and so on. So it's like a loop. So this is nice. Now, like, you can use that choice name instead, and it becomes the comma operator becomes your infix operator. There's also another thing that I discovered when I implemented this, was when I tested it, it failed to compile when I was passing in just a free function as the first parser. And at first I didn't understand why, but then I realized if you're passing in a function as a template parameter, what are you really passing? You're passing a function pointer, right? What's a function pointer? It's just a pointer type. And the core language doesn't have the bitwise operators defined for pointers. That wouldn't make any sense. So, and we cannot just override that rule by implementing our own. So the way I got around that is with a compile time check, an if const expr here. So if it is a pointer, then I just wrap that pointer in a lambda that does nothing but just call it when you call it, and then it compiles. So those are kind of ugly things you have to deal with in C++, but it makes this function more useful. Okay, so this parser combinator, this slide I think is the most important one in this whole talk. So if you miss a lot of the other stuff, but you get what this function does, then you kind of have grasped some really profound things in functional programming. So this is also a parser combinator that combines two parsers, but we're not passing in two parsers. We're passing in one parser and a function. So what kind of function? Well, you can see in the concept, it has to be a parser combinator. And it's a parser combinator that takes one argument of the value type of the first parser. So why are we doing that? Well, again, first we try the parser. Then, if it's successful, we invoke this function, this parser combinator, and we pass in the parsed thing. And since this is a parser combinator, it will return a parser. So this is the second parser. And then we immediately parse with that one on the rest of the string. So we are combining two parsers, but we're being much more smart than just passing a second parser directly. We're being lazy about the choice of the second parser. And since this second parser actually gets the result from the first parser, we can make this function incorporate the result of the first parser if we want to, or we can make a function that chooses what the second parser should be based on what the first parser has seen. So that allows you to do some really cool stuff. You can parse languages that are not context-free. So these languages where the rules change depend on what you have parsed. So that's really advanced stuff, but we're not going to use it, but it's kind of cool to know that you can do that. So the simplest example, if we parse item, the item parser, and combine it with the unit of char parser combinator, what would happen? So item would parse, we have foo as inputs, item would parse the f gets passed in to unit of char, which just gives you the parser that gives you the f back again. And then we parse with that, so we get the f. So actually putting unit of char here on the right side has no effect. So there's an important relationship here between this operator and unit of char, kind of similar to how empty doesn't do anything on the, with choice. So I decided to give this a good name as well. I kind of like the name chain. So you can think of these parsers as kind of links in a chain. If any of these parsers returned by the parser combinators fails, this whole chain of parsing will fail, and we just undo everything. Yeah, one thing I forgot to say also, note that this function chain is, this is template. But that's another nice thing with C++20. Now you can, if you have, yeah, you can use auto parameters now for functions like this, if they are simple. So I think that syntax is real nice, and you can, so this was called automatic template deduction. And you can also constrain these auto parameters. So this is just like with the generic lambdas. You could write lambdas with auto since, was it C++14, I think. Now we can also do this with free functions, which is really nice. Okay, so, yeah?
Why didn't you constrain funcs?
Yeah, actually, yeah, that's a good question. Why did I constrain funcs? I didn't come up with a way to actually do that. Since it's a variadic argument, I'm not sure how to do that. And they are also like the types will be depending on this. The return types could be depending on the function. We could talk about it later perhaps, but yeah, I couldn't find a good way to do it here. All right, so these choice and chain functions are very useful together. So suppose you want to write a parser called skip. It's almost exactly like choice, but the idea here is just we parse with parser p, and then we just throw away the result, whether it succeeded or not, and return the result of q. So you could implement that. That's fairly simple. So if you skip item and use unit of x of foo, then you would get x and the o's, right? But now you could also write this as a one-liner. Just combine choice and chain. So the easiest way to see how this works is imagine that the first parser p succeeds. So chain would parse with p. The parsed thing goes into this little lambda, which is a parser combinator, which just throws it away and returns the second parser q. And then we will parse with that. So this is the first branch of the if. If the parser p fails, the whole call to chain fails, and then we will, with choice, we'll try the second parser q. That's the other branch. So these are really extremely powerful functions. Here's another example. Suppose you want to parse a digit, just a single digit. So it's just like the item parser, except there's an extra check. So if you have a character and it's a digit, so we can use is digit here, then it's successful. So that's easy to write. But what if you want to parse something different? Maybe you want to parse a lowercase letter instead. So as you can imagine, you could write that. You take this function, you call it lower, and you use is lower function instead. But then you realize you want to parse uppercase letters. So you copy this function, you call it upper, use a different predicate. So you start to realize you have a code duplication, right? This is all the same function. It just varies with the predicate. So you might think, okay, so what if I make a parser that takes that predicate as the input and just check it? Can you do that? No, you can't, because then it wouldn't be a parser anymore. A parser has to take a single argument, the input. So you have to write this as a parser combinator. And maybe it looks a bit scary because there's two nested lambdas here, but I call it satisfy. So satisfy takes a predicate and a parser. We can even default that to be the item parser. That's the most common case. And so what's a predicate? Well, we have also a concept for that. It's just a more constrained version of regular invocable. So std predicate means it's a regular invocable whose return type is Boolean testable. So that it could be bool, but the return type doesn't have to technically be bool. It could be a type that's convertible to bool, and it has to have a negation operator whose return type is also convertible to bool. So it's a bit technical, but yeah, it's a function returning a bool. You can think of it as that. So satisfy, what will it do? It returns a new parser using chain. What will this do when we call it? It will first parse with our parser. We get the parse thing passed into this outer lambda, which is a parser combinator. Then we return a new parser, which has captured the predicate and the thing. And when we parse with that, we will check the predicate on the parsed thing and succeed or fail. So once you have defined this function, it becomes really trivial to parse digits, because it's just a call to satisfy with the predicate and the implicit single character parser. If you parse lowercase, satisfy is lower. Parse uppercase, satisfy is upper. What if you we want to parse letters? Well, letter, what is it? Either a lowercase or a uppercase symbol, so you can just combine them with choice. An alphanumeric character, that would be a letter or a digit. So here we're starting to see, like with these basic functions, it becomes very nice declarative code here that really explains. You just need to read it and you should see what it does very easily. It's also useful to have a parser combinator called symbol. So the idea is you just give it a character and it returns a parser that checks if it matches that exact character. So you could also write that. And then you can easily, if you want to parse plus, you just call it symbol plus. So, okay, so far we have done some pretty simple parsing with just single things. So, but sometimes you want to parse multiple things. You want to apply a parser multiple times, as many times as you can, without, as many times as you can, and then combine those into one thing. So for this we need iteration, and this is a little bit more difficult. This parser I have to define as a class, because there's stuff to capture, but we also need a name for it. If we're going to use recursion, we cannot use a lambda, because we need a name for the thing we call recursively. But basically it's not that complicated. It's just a function again, with a function call operator. So we start reduce many. It takes some initial thing. It takes a parser, and it takes a function. And if you look again at the concept at the top, the function has to be a function that takes two arguments. The first have to be the type of the initial thing. The second have to be the type, the value type of the parser. And what we do, again, we can combine choice and chain here. So when you give some input, we will first call the parser. We get a parsed thing. Then we pass that thing together with the initial thing into this function. So this function can combine these two. Like it's two characters, combine them into a string. And that gives us our new initial thing. And then we can recursively make a new reduce many parser from that. And so this will effectively, this will call recursively the same parser, concatenating things with our function until it fails. And what happens when it fails? Well, the second option of the choice kicks in and it gives us back the initial thing, which will be the thing we have combined so far. So of course this would be easier to write as a loop in C++. This isn't terribly efficient, but I think it's kind of interesting to see how you can do this. So there's no state here in this thing, except for the state you start with in the constructor. Everything is constant, and yeah, so it's pretty interesting. So we can make a little helper function for this too, which is special. This is just for character parsers, so I call it many. So many will start with an empty string, parse with our character parser, and with this little lambda here, the third argument will concatenate the result into a string. So now we can parse, for example, many many symbol plus. So that will give you a parser that parses 3 pluses from the beginning. If there's no pluses, we get the empty string. Okay, so we can parse many things now. That's useful if you want to parse white space. So white space, what is that? It's many satisfy is space. Very simple. It's useful if you want to parse tokens. What's a token? So it's something we parse by skipping some white space, applying our parser, and skipping some more white space after it, and then returning the parsed thing. So we can use chain here. So now we can parse, for example, foo bar. It will strip the white space before and after, and we just get the foo. Now, sometimes you don't want to parse a thing 0 or more times. You want to parse it 1 or more times. So we want the same result as with many here, but except in the second case, when we have no pluses in the beginning, we want to fail instead of returning an empty string. So that at first seems simple. So we just need to first use chain again, call our parser, we get the first character. Then we use many to call the rest of the characters, and then at the end we just need to concatenate the first character and the rest of the string. And unfortunately that doesn't work. And I hope you can see why it doesn't work. The problem is we do have the string from many, but we don't have the first character. That was passed into the previous lambda, which we never used it there. We just threw it away. So it's lost. We cannot access it in the lower lambda. So that's a problem with chain here, right? If there's just one lambda, there's no problem. But if you have multiple ones, you can only access the thing right above it. So how can we solve that? So my first thought was maybe we can just make some kind of smart parser that combines many with the first character and pass it along. It works, but it's not very nice looking. Another thing we could do is make this sum into a class instead, so we can have a private data member where we can store that character, so then we can access it later. But that doesn't feel like a functional solution, so it turns out the general functional solution here is much more interesting. All we need to think about is we don't have this problem if we just had one lambda, so how can we merge these two lambdas? A simple way to start is just to wrap them in a new lambda, right? So you just write a new lambda with the same function signature as the first one, and then you're fine with the access, right? You have the character because it's passed in, and then you capture it in the bottom lambda, so it should be accessible. But also it won't compile. Now we need to return something in this lambda, and we still have the two inner ones to combine. And we want to call them one after the other, so we only have one function to do that. We have to call chain again, right? But that doesn't compile either, because chain has the wrong function signature. The first argument to chain has to be a parser, and now it's a parser combinator. Oh, that's a problem. But actually, when you think about it, what's the first thing you want to do here? Well, you just want to call that parser inside there. So let's just remove that first lambda and just keep the return value. And now it works, right? The character gets passed in. So you first parse with the parser, then you parse with the many parser, you have captured both things, and it works. Great, so now we can parse natural numbers. What's a natural number? It's some digits. 1 or more digits, remember that. But we don't want that as a string. We want it as an int in this case, so we can use chain to convert that into an int with s2i. So now we parse natural numbers. What if we want to parse an integer? What's an integer? Either it's a natural number, now we have a parser for that, or it's a minus symbol followed by a natural number, and then we just want to negate it. So here we're also using two lambdas with a chain, so sure, you lose that minus symbol, but in this case it's fine, because if we see the minus, we know what we want to do. We just negate our natural number. Okay, great, so now we can parse integers, and it works. I actually want to stay a little bit on this chain function problem, because it's very important. Here's another example. Suppose you want to parse 3 integers with white space. So you just want to apply token integer 3 times and then add them up. So that seems straightforward to write like the left version. Unfortunately, it doesn't work because you just have the last integer at the end. So what you have to do, you have to apply this trick of combining the last 2, and then you get a new lambda, and then you combine that, and you get that code on the right, which actually works. It solves the problem if you have the captures in the right places. But it comes as a trade-off, right? You want to be able to write the code on the left if you can. The code on the right does multiple calls to chain, so there's some performance issues there. There's extra captures. And of course, it looks very ugly to have this deeply nested code, right? You get a whole like trail of sad emojis at the end. So that's not code you want to write if you can avoid it. Sometimes you can write a bit of a hybrid between the two, and in principle you could go back and forth. It's the same thing, but the right version is the general one that always works. So can we do something about the ugly syntax? Well, if you're prepared to cheat a little bit with standard formatting tools and so on, we can sort of rearrange it a bit. So if we just move things over, so the important stuff is on the left, the parsers, and the kind of boilerplate stuff is on the right, then it becomes easier to kind of see what we're doing. We're calling these 3 token integer, we call the result x, y, and z, and then we add them up. Okay. So that's a little bit of cheating, but it actually is interesting to look at that code, and it becomes, I'm going to do something here. I'm going to hide a bit of the code, so I don't want you to look at the gray stuff. That's the uninteresting stuff. If you just read it as if you had this code, the color part, it's very, very nice and clear to see what you do. There's some interesting aspects here. First of all, I mean, this is pure functional call. It's just a function call. But it kind of looks like imperative code, right? If you look at it as a series of statements. It's actually also imperative code with a bit of a bonus, because we know that if chain fails, if any of these parsers fails, then we will just abort and not do the rest. But we don't have any checks here, right? So this kind of reminds me of another feature in C++ that's I don't even use here. I don't know if you can see it, but think about exceptions. So with exceptions, you can write a try block with nice kind of linear code, no if checks. And then if an error happens, you will jump down to the catch part and deal with it there. This is a little bit like the same thing, except the error would be percolate up to the caller instead. So I think that's an interesting observation. Another interesting thing is, of course, this is a pure function call. If you just made this a return of a function, it will always return the same chain of parsers, no side effects. That would be the case even if the parsers themselves had side effects, because we're not actually calling any parsers here. We're just combining them. The calling will happen later when we call this combined thing. So this is a great way to deal with side effects in functional languages. And in Haskell, for example, if you have a function with side effects, you cannot even call it in the normal way, at least. But you can compose functions and have them be called later. So that's a trick in Haskell to deal with side effects. You sort of compose the functions and delay the side effects as long as you can, down to like the last call in your main. That would be where you set off everything. But yes, it comes with this ugly syntax overhead, and there's no great way to get around that in C++. In Haskell, they invented a special syntax for this. And if you've seen a Haskell code, you've probably seen this do notation. And this is how you'd write the same thing in Haskell. And it looks kind of similar, right? So you have this special keyword in Haskell do. Then you just list your parsers. If you're interested in capturing the results, you can use this left arrow. And then you just add them up at the bottom and call the function called return. So 2 things. If you haven't read Haskell code before, this token integer, that's a function call in Haskell. So in Haskell, you don't put any parentheses or commas, you just put name and arguments with white space. So it's extremely terse, kind of hard to read in my opinion, but I guess you get used to it. So this parenthesis at the bottom has nothing to do with function calls. It's just evaluation order, like in math. You add up those things and pass them as a single argument to a function called return. And return, that's also a thing in Haskell, it confuses me a lot. There's no return keyword in Haskell. So name return, this is just a function. And of course, it's the same as my unit function. It just returns that wrapped sum as a thing. Haskell doesn't need a return statement because functions are just a single expression. So that's what it will return. But in Haskell, it has to be called return to work with this do notation. Okay, so many people looked at this, and of course, people have proposed that C++, it would be really great if C++ had something like the do notation. Then we could do this nice functional composition thing. It could be useful in many other cases than parsers. Okay, so is that a good idea or not? I don't know. Potentially it's a good idea, but I also have very little hope that this will make it into a standard, at least anytime soon. There will have to be a lot of underlying work to motivate it, and I just don't think it's high enough on the priority list of the standards committee to do that work. So maybe a few standards in the future, but yeah, I guess we'll have to wait and see. But I'm actually also not very concerned about that, because it turns out we can write a parser combinator thing that looks even nicer than the left-hand version up on the top. And we don't need to use any new features, just C++20, and we get most of the functionality of the do notation. We just have to find out a little different way to express this. So that gets us to the last point from the beginning, which is applicative parsing. So, partial function application, what's that? Well, if you have a function in C++ that just takes 3 arguments, of course you have to call it with 3 arguments. Otherwise it couldn't compile, because how could it compute the sum? But if you worked in a functional language like Haskell, you know that in Haskell you could actually call a function and not pass in all the arguments. So what would happen is you get back essentially a lambda that has captured a pointer to the original function and those arguments that you passed it. And it will take as many arguments as you didn't pass. So when you pass that with the remaining arguments, it ends up calling the original function, passing in first the capture arguments and then the rest. So that's partial function application. And you cannot do that straight away in C++ because that's not the way the language was designed from the beginning. But we can easily emulate this. We just need to write a simple helper function. And I chose the name papply for this, so it means partial function application. Don't confuse this with standard apply, which does something different. So it's just a function that takes a function and a bunch of arguments. And then we can make a check, is this function invocable with those arguments? Well, if it is, then we're happy, we can just invoke it like normal. But what if it's failed? If that concept check fails, then we're going to assume that that's because you didn't pass in all the arguments. So then instead we pass it into standard bind front. That's a new function that was added in C++20. So it's like standard bind, but a little less general, although it has a much nicer syntax. So you just pass it a function and a bunch of arguments, and it will return a new function that has capture everything, and then you can call that. So that's what we want to do, except when we could just have called the function with all arguments. Note also that papply here, it's using another new feature from C++20, which is now you can write generic lambdas with explicit template parameters. So instead of auto parameters, I have used name template parameters, which is a little bit scary. Now we can use lambdas with all those 4 bracket styles. But I actually think this is a nice feature. It simplifies language, not by itself, but if you think about this, combined with that abbreviated template syntax for free functions, it sort of unifies all these the ways you can make template functions between lambdas and free functions. So I think it's a nice feature to make them more similar. Okay, so with this, now we have the option. If we have a function like sum3, we could call it as normal, just pass it to papply and call it once. But we can also go the other extreme. If we have this function with 3 arguments, we could call it 3 times with passing in 1 argument at a time, like at the bottom here. And that's known in functional programming as currying, which you probably heard about. It's named after Haskell Curry, the same guy that they named Haskell after, theoretician who came up with this stuff. And now, so we're armed with currying in C++20. And that's really great, because now we can write a new parser combinator. So I use the last remaining bitwise operator here, the XOR. It looks scary, but it's really simple. You just call, you give it 2 parsers. First we invoke the first one, call it PR, the result. Then we invoke the second one, call that QR. And then we pass PR and QRs, the parsed things, into papply. And that's what we're going to return if both are successful. Okay, so we're going to make a helper for this as well. So I like to call this sequence. So sequence takes a function and a pack of parsers. It has to be as many parsers and of the right value types so that we could actually call that function with the parsed things. So what we do is we just use our operator. We turn function into a parser with the help of unit and then pass in the parsers. So it really hurts your brain if you try to think about what this is going to do when you call that big return parser. But essentially what we're going to do is we're going to parse with the unit of function, which is going to unpack the function. Then we're going to partially apply one of the parser's results all the way to the end. And at the end, we'll end up calling the function with all those parsed things as arguments. And that's really nice, because now we can write this sum3 parser. We just sequence 3 calls to token integer. The parsed things end up in the lambda on the top as x, y, z. And then we just add them up and return it. So if you compare this to the do notation in Haskell, it looks very similar. Except, the biggest difference, I guess, is that the sum ends up on top, inside of a lambda instead of at the bottom. And of course, those 2 returns, you have to remember, they don't have anything to do with each other. But this is really cool because, yeah, this code is quite readable, I think. And now we can write sum3 parser, and yeah, we can test it. Yes, we have a question here.
Yes, you could return some synthetic logic from sequence with a load like index or call operator, and this should accept lambda.
Oh, interesting. You spoke right over my head, but yeah, let's discuss that. Yeah, I'm sure there are many other ways we could do this, but yeah, really cool. Actually, if you are interested, you can do as an exercise, try to implement this operator using chain. It actually makes the function look a lot nicer and simpler. And it also kind of proves that chain is a more general solution, but it also comes as a little, there's a little performance cost there. So, but yeah, something you can think about. And this is nice. Now we can go back and rewrite some of our parsers. So this sum parser, the first case where we use this nested chain trick, we can instead rewrite this as a sequence. Sequence of parser, many parsers, we get the character and string, and we add them, or concatenate them on top. You can do this with most of the use cases of chain I showed before. Not all of them, but most of them. Right. So it's a lot of code, I know, but think about this now. You can take basically all the code I've shown you, just stick that in a header file or a module file if you want to be really modern, and you have basically a complete parser combinator library. Maybe there's a bit more work if you want to make it a great library, but all those things are general purpose useful things. So now we're ready to actually parse what we wanted to parse from the beginning here. Mathematical expressions. So we import this library of functions. We already know how to parse integers. We made a parser for that. So we just need to parse expressions, terms, and factors. So we need to write 3 parsers. And since they are referring to each other, we have to declare them first as free functions and then define them. Okay, so we first declare them. Pretty simple. So here's the first parser, expression. What should it be? It should parse a term, a plus sign, an expression, or a term. So it's a choice between a sequence starting with term plus expression. We keep the term and the expression and we add them. That's the result. Or if that fails, it's just we check if it's a single term. Okay, same thing with term. It's a factor, multiplication sign, term, or a factor. So it's a choice between a sequence. We keep the factor and the term. We multiply them. Or it's a factor. And finally, factor. It's a left parenthesis, expression, right parenthesis, or an integer. So again, sequence, we just keep the expression and return it. Or it's an integer. And here also, it's not expressed in the grammar, but since this is a sort of innermost non-integer then we could actually get rid of all the white space with help of token. And we're done. So now we can parse expression. So here are some tests. 3 times 2, 4 plus 2 should be 14. If you use parentheses, it will compute 18. If we try a negative number, it will work as well. We could add some redundant white space and parentheses. It still works. If we give it something it doesn't recognize, like subtraction, we didn't implement that, then it will get the first factor, but the rest of the string, there will still be something left. So on the top level, if it doesn't parse everything, you probably want to treat it as an error. And finally, of course, if you pass like 3 as text, it will also fail. So first example, but it's a little bit of a toy example, right? So we want to do something cooler. Yeah, but first, just for fun, here's the Haskell code. And you can also observe here, it's very, very terse. Here it's using the do notation instead, but it is the same idea. That curious operator at the bottom, that's the same as my pipe operator. So Haskell has lots of these strange operators that do different things. But you can see how nice it is. It's pretty straightforward to go from the grammar to just writing the code. Almost mechanical, you might say. So what about parsing grammars themselves? So here's another example. This is really interesting example. This is the original, this is from Wirth's original article. And it's the example he used to describe the syntax of his language. And it's a cool example because if you look at it, first of all, it uses the different syntactic constructs. But what does it describe? Well, it actually describes how to parse itself. So we have on top a syntax is a number of productions. So each of these lines is a production. So production is an identifier, equal sign, expression, dot. So you have identifier is production, the equal sign, the expression, and the dot at the end. And then you have an expression. What's that? It's one or more terms separated by the option. A term is one or more factors. A factor is either an identifier, a literal, parenthesized expression. So parenthesis is just for evaluation order, again, like just in math. Or it's an optional expression, or it's a repeated expression. And finally, a literal, that's a non-empty string of characters surrounded by quotes. So he uses 4 quotes, so you have the quote with a quote as an escape symbol. So he uses quote as escape and string, and then surrounded by quotes. So I mean it's literal quote. So this is actually describes it all. There's 2 things missing. There's no rule for identifier, but you can define that as maybe a number or a letter followed by numbers or letters or underscore or whatever you like, and a character, which is any character in your character set. So that's what the item parser would understand. So if you think about it, so what if you can just implement a parser for each of these rules or each of these productions? Then we could parse grammars themselves, and we can parse them into any kind of data structure we like. So what if we parse it into a data structure and we equip that data structure with some serialize function that prints out something? Then we can make it print out the source code for a parser for this language. So we would have written a parser combinator, parser generator for other parser combinators. And even cooler, if you give this particular input to that parser combinator, it should essentially print the source code of itself, minus a few things. So that was really fun to try. So here's just one example. This is just one of the parsers, the production parser. So identifier equals size expression dot. So I parse identifier equals expression dot. And I just keep the identifier and expression and this AST production. These are just simple structs that I created that makes my abstract syntax tree. And then I have a print function for this. And what happens if I give this production function the contents of the comment on top and then print the resulting AST, then it will print the version on the bottom, which is more or less identical to my function. The only thing you have to add is that what's inside of this lambda, what you want to do with the result, and a few details like that. But that's really nice, I think. Okay, so now that we're armed with this, we can go in further and try to implement some big parser. So what about parsing C++ itself? Okay, so that's quite a jump. C++ is notoriously difficult to parse, as you probably know. It's not a context-free grammar. There's many ambiguous situations. Actually, if you look in the standard, it's described in great detail how we parse C++. There's, I think, 9 separate translation phases. So you go from stripping white space and comments, and then the preprocessor, expanding macros, and you deal with templates and resolve ambiguous situations. So it's really complicated. It's nothing I would recommend doing as a hobby project. I didn't try it myself, but I decided to try something a little bit simpler. So I knew that in this book, Elements of Programming, at the end there's an appendix written by Sean Parent and Bjarne Strostrup. And so what they do in this appendix, they define a simple language, and this language is a pure subset of C++. So it's missing a lot of features that you even find in C, but it's not a toy language. It's a complete working language. You can actually compile it with any old C++ compiler, and it was a language that was used to implement all the code in this book. And if you know this book, it has some pretty sophisticated code in it. It basically explains how you implement something like STL. So it's a really instructive language. It's a great language if you want to write like a book or a paper and you want to explain some algorithms. You could use pseudocode, but it's cooler to use real code, but maybe you don't want people to have to understand all of C++. So this is like a very simplified C++. And I think it's also instructive to see that they managed to describe the whole language in 9 pages. This is about 200 times shorter than the C++ 20 standard. Of course, it's not a fair comparison. The standard has to go into all these technical details. This kind of glosses over this, but I think it's kind of interesting anyway. And Sean Parent, he also wrote a handwritten recursive descent parser for this to test the code in this book. You can get that code on his GitHub. You can also actually get this book for free nowadays. You just go to that link and download it. Check it out for yourself. And so this whole language, the syntax is described on these pages. It's 60 of these productions in this Wirtz grammar language. And so we just need to implement 60 parsers. Of course, if you have that parser generator, that would help you. But I was stupid. I implemented this before by hand to see if it was possible. And here's one example. This is a parsing of a while statement. So it's while, parenthesis, expression, parenthesis, statement. So all of these functions are simple parsers to write like this. It's very straightforward. All right, so I have a quick demo to show this. So what I did was I made a little tool. So this is just a toy thing. What you can do here is you can give it single line declaration in this subset of C++ and check if it syntactically is correct. So it's a test for my parser here. So we can try something like, if I make a function, I don't know, foo, takes an x, and let's return, I don't know, 2 times 3 plus x. Put some extra white space. That shouldn't be there. Okay, does that look like correct syntax? Oh yes, I missed semicolon. Oh, I hope that didn't break things. Parsing successful. Okay, looks okay. Now I can actually format this code as well, kind of pretty print it. So I have just a serialize function for this. And this is like, yeah, compact version, so just so we see that it's correct. You can also format this in a JSON format. So this shows you the whole abstract syntax tree. This is kind of thing if you're implementing a compiler, you would be interested in seeing all this. You can also kind of simplify this tree a bit, so you have like a prune function, takes away some redundant stuff. So now we see simplified tree here. So you see it's a declaration of a procedure. It has a return type of int. This is a name, which is an identifier called foo, and so on and so on. And I also did some constant folding here. So if I format this again, I simplified it. So things like 2 times 3 become 6 now. This is kind of thing a compiler would optimize on this level. So let's try something a little bit more advanced. So let's make, I don't know, template. Type name T. We can even have, this language also has constraints or concepts. So we can try requires. It looks a little bit different than in C++20. Let's pretend we have a concept called integer. So you write it like that with parentheses. The trick is you just can define this as macros that is compiled to nothing. And then, so it doesn't really do the check. And then we make a struct. And let's make a data member, tx. And let's try the constructor. So we should initialize maybe x to 42. Body of the constructor and the end of the class. Does that look correct? I think so. Yeah, it parses. Yeah, it looks okay. We have the JSON. We can prune it. Show it again. Yeah, this time try an enum. No, ABC. Oh, it failed. Okay, enum. What am I doing wrong? Okay, so you can see. Anyway, live demos. So I have this on GitHub. You can try it out. It's actually like, if you think about it, if you want to write your own toy compiler or like a C++ interpreter, or maybe you have your idea for your own programming language, like a dialect of C++ or something, this could be a little tool you can experiment and yeah, try changing it and see, and yeah, write some tools. You get the parsing done for free, so yeah. Should be fun to use. So we're at the end. So I have some takeaways here. Some kind of positive things in my mind is, I think at least that C++ is a language that supports a functional style of programming. At least syntactically, I'm not missing a whole lot. But yeah, of course there could be improvements. Also, I think it's cool that C++, it's not just, there's not just one functional language in C++, there's kind of two. So you have your regular runtime functional language, but you also have your compile time functional language using concepts, alias templates, value templates, and so on. With every new version of C++, this, I mean, it's been known for a long time that C++ templates is a functional compile time Turing complete language in itself. But with new features, it feels more and more like a natural language to use. Some kind of neutral feedback, I think that, you know, it's, yeah, there's many variants of callable types in C++, which really complicates things for beginners, but you know, it's due to the long history of C++, and they all have their uses. It's not like lambdas make classes with a function call operator obsolete. Sometimes you need them. And things like std invoke help a lot there. Also, of course, I mean, pure functional C++ code will never be as naturally terse as Haskell, or a language that was designed for functional programming. So if you really want to work in this pure style, maybe go ahead and use a functional programming language and not C++. Also, there are some problems. First of all, you have to think about performance. This is C++ after all, so it may easily suffer. For example, in C++ standard, there's no guaranteed tail call optimization. And so if you look at this do notation in Haskell, you might think, oh, that's just syntactic sugar that does all these recursive, like deeply nested function calls. But actually, those function calls are all tail calls. So they are relatively easy to optimize away by the compiler. And Haskell guarantees that that is done. So even if you can think of it as you can just program in a pure functional way, but the compiler will turn it into imperative style code with ifs and whatnot. But you never see that. In C++, there are no such guarantees in general in the standard. I think there are some compilers have some intrinsics and notation you can use, but before, if you want something like do notation in C++, you probably first need to make sure that you can guarantee tail call optimization for performance. So there's a lot of this technical work that will have to be done. Also, it's easy to accidentally do a lot of extra copying of objects, like all these lambda captures. I just capture by value, so maybe you want to use like perfect forwarding and move semantics and think about things like that, which you don't need to think about in Haskell, for example. Unfortunately, also, this is very, very hard work for the compiler. The compiler will really hate you if you try to write the code like this. So I didn't notice this at first, like writing the number parser or the grammar parser, it worked just fine. And I was using GCC 10, I believe, when I started this. But when I implemented this EOP parser, I started noticing the compile times were getting awfully long. And when I was exactly halfway, so at the 30th function, the 30th parser, it started eating up all the memory on my computer until the compiler just crashed. So I thought, okay, this is the end. But I just decided to try switching over to Clang instead. And for whatever reason, Clang does something different. I don't know what. But it still managed to compile it. So very long compile times, but it still worked. And I managed to get all the second half of the parser done. But it's still like ridiculous compile times. It takes maybe half a minute. And it's a very small program on this computer. So you have to be aware of that. This does not really scale that great. I also tried it in MSVC 2022 recently. It also ate up all the memory and crashed or failed. So compiler writers have some work to do if they want to support this. And if someone knows a lot about debugging compilers and can tell me why Clang can handle this and the others can't, it would be interesting to investigate. Right. Also, I mean, if you think about it, there's all these little lambdas created. So try to compile it in debug mode, you'll get megabytes and megabytes. I think like 25 megabyte binary for this very small program, really. So yeah, there are problems. Okay, so we're at the end here. So I have some links. Link to this talk. You can find the PDF. You can also find the code for this virt parser, EOP parser, and the number parser. You have all the code in the slides. And feel free to use them for whatever you like. It would be fun to see if you can come up with something cool, so please tell me. I also included some links to some people that you might check out if you're interested in functional programming in C++. I think these are some people from the community that are worth looking at. So Bartos and Ivan, for example, have written some great books about functional programming in C++. Ben Dean, you might remember in CPPCon 2017, he did a keynote with Jason Turner from CPPcast called Const Expert All the Things, kind of a famous talk, where they showed how to, Ben had used this parser combinator technique to write a pure compile time JSON parser. so you can use like JSON strings like CompyThon switches in C++ code. So the focus on that talk was const.expr. So they kind of quickly went over the parser stuff. But you can look at the code and you look at the talk, you can see it's exactly what I did. But it was in C++14, so you don't really need C++20 for most of this. But the code looks so much nicer now than it looked back then. Also, like Jonathan Miller, he has written a parser combinator library called Lexi, I think. I have never used it. It's the same idea, but it's a completely different design. So for sure, like many people have done this before. And so if you want to learn more, you should definitely check out their versions as well. And finally, like Cy Brand has also talked about this a lot, and is one of the champions of functional features in future C++ standards. So yeah, that's it. So any questions, any comments, ideas? Like, what do you think? Is C++ a functional language? Yes, no? Yeah. Definitely, yeah. All right, so thank you.